Hello everyone, welcome to lecture Digital Logic Design. I am Dr. Velayat Khan. In today's lecture, I will explain decoders and demultiplexer and encoders. Uh, let's first talk about decoders. What are decoders? So decoders converts binary information from n input lines to 2 raised to power n unique output lines. Normally decoders are n to m decoders where m is normally less than 2 raised to power n. So there are n inputs and there are m outputs of the decoder, but m, which are the number of outputs, is normally less than or equal to 2 raised to power n. So for n inputs there can be maximum of 2 raised to power m outputs, 2 raised to power n outputs, but in some cases the number of outputs may be less than or equal to 2 raised to power n. So this is a typical decoder which is most frequently used in digital logic design. So this is a 3 to 8 line decoders. A decoder basically generates minterms from the input lines. So in this example there are 3 input lines, x, y and z, and there are 2 raised to power 3 which is 8 AND gates, and each AND gate generates a minterm. As we already know, for n variables there are 2 raised to power n minterms, and in this decoder there are 3 inputs and 2 raised to power 3 are the outputs. So this decoder include an AND gate for every minterm. So in other words, every AND gate is responsible to generate a minterm. So there are 8 minterms and there are 8 AND gates. As can be seen on the right side of the diagram, when x, y and z are 0, 0, 0, then this correspond to minterm 0, and that is x prime, y prime, z prime, and we also designate this output with d0. So this is actually the 0 output of this decoder. Similarly, when x is 0, y is 0 and z is 1, then this represent the second minterm, which is d1, x prime, y prime, z. So this is the second minterm, and we call this the second output, or d1 of the decoder. And similarly, this is the third minterm, this is the fourth minterm, fifth, sixth, seventh and eighth minterm. So there are 8 minterms, and every minterm has been generated by the AND gate of the decoder. So in this case, every input is also complemented, because in the minterm every variable can appear in the normal form and also in the complemented form. So to create all possible minterms, it is necessary to create the normal form of the variable and the complemented form of the input variable, and this is the case for all input variables, for x, for y, and for z. So this is a 3 to 8 line decoder which gets a 3 bit input and give 8 outputs. One more important point about the decoder is that whenever an input is applied to the decoder, only one output of the decoder is 1, all the rest of outputs are 0. So this is a decoder implemented with the AND gate. So in this case, when an input is applied, only one of the output is 1, all of the rest of outputs are 0. And which one would be 1? That is very clear from the minterm. When the input is all 0, for example 0, 0 and 0, then this combination would provide all the inputs to the first AND gate 1, 1, 1, and this would give 1 at this first output d0, and all other outputs would be 0, and that is because at least one of the input to these AND gates would be 0. That would make the output of these AND gates as 0. So whenever the input is 0, 0, 0, only D0 would be 1, all the rest of the outputs would be 0. When the input is 0, 0, 1, this corresponds to momentum 1, so only D1 would be 1, all of the rest D0, D2 and until D7, all of them would be 0. So the main property of the decoder is that whenever an input is applied to the decoder, only one of the output would be 1 and all of the other would be 0. And remember that whenever this is true, only one of the output would be 1 when the decoder is implemented with AND gate. If it is implemented with NAND gate, then only one of the output would be 0, all of the rest would be 1. We would see an example of the decoder implemented with NAND gate. The block diagram of such a decoder would look like this. This is a 3 to 8 line decoder. So a 3 to 8 line decoder can also be written as 3 cross 8. So this is actually the organization of the decoder. So whenever 3 cross 8 is written, then it means this decoder has 3 input and 8 output. These output can be designated with D0, D1, D2 and D7, or internal to the block as 0 to 7. So these are just 8 output lines, and the variables can be different. Variable can be assigned to these output lines. There is a truth table for the 3 to 8 line decoder as well, and this truth table is very easy to follow. As we can see, this decoder, 3 to 8 line decoder, has 3 input and 8 output lines. So in the truth table we would have 3 input variables and 3 columns for the inputs, and similarly for the outputs we have 8 output variables. We call them D0, D1, D2 and until D7, and these are the 3 inputs X, Y and Z. So whenever all the inputs are 0, only D0 would give 1, and all of the other outputs would be 0. So this is the combination when the input is all zeros, and the output we will have only 1 for D0 and all other would be 0. So similarly, if the input is changed to 0, 0, 1, then only D1 would be 1 and all other output would be 0. When the input is 0, 1, 0, the only D2 would be 1, all other would be 0. And similarly for all other input combination, and at the end it would create a diagonal of outputs. So whenever the input increases, the value of the input increases, the higher output gives 1 and all of the rest would give 0. So this is the truth table of 3 to 8 line decoder. Now there is a decoder is very important circuit, and it has been used in many applications. Here I give a simple example where BCD-to-decimal decoder is designed. So this decoder would get a BCD digit encoded in the BCD code, and it will give us a decimal digit. So it's a BCD-to-decimal decoder because decimal digits are encoded using BCD. So the decoder would decode the encoded BCD information. So whenever this decoder would get a 4-bit BCD coded decimal, it would decode and generate the actual decimal which has been decoded. So this kind of decoder would have a truth table just like the one we saw on this slide, but the difference would be that on the contrary, we would have 4 inputs. In this 3 to 8 lines decoder, we had 3 inputs, but in BCD to decimal decoder, we would have 4 inputs, and those inputs would be W, X, Y, and Z. Similarly, as this is a BCD to decimal decoder, and we already know that in the decimal there are 10 digits, so there would be an output for each digit, and there are 10 digits, so there would be 10 outputs. So just to compare with 3 to 8 lines decoder, as we have 8 outputs in the 3 to 8 lines decoder, we would have 10 outputs in the BCD to decimal decoder, and those outputs would be D0, D1, D2, D3, D4, D5, D6, D7, and there will be other 2 columns for D8 and D9. So creating a truth table for BCD to decimal decoder is quite easy. And one more thing which is quite similar to this 3 to 8 lines decoder is whenever the input W, X, Y, Z is 0, only D0 would be 1, and whenever the input is 0, 0, 0, 1, then D1 would be 1, and just this diagonal would be enlarged to D8 and D9, and the rest is pretty the same to the 3 to 8 lines decoder. So I'm not creating BCD to decimal decoder, but it is quite easy to create one. Now, how can we derive the Boolean equations for the output of BCD to decimal decoder? As I mentioned, in this BCD to decimal decoder, there would be 10 outputs, D0 to D9, and each output would represent a single digit. And the 4 inputs W, X, Y, Z are the 4 bits that represent the decimal digit encoded in the BCD. So to derive Boolean equations for these 10 outputs, we can create a Kmap for each output, but as we saw in the 3 to 8 lines decoder, only one output is 1 and all of the rest are 0. So this feature allow us to use a single map for all these 10 outputs. As this map has already been shown on the screen, but I will just tell you if you would if you would be using a Kmap for every output variable, then that would look like this. We would create a Kmap for D0, and as D0 is 1, then only the first minterm would be 1 and all of the rest would be 0, just like in the Kmap. This is the Kmap for 3 to 8 lines decoder, and D0 is 1 only in the first case. When for the first minterm it is 1, and for all the rest it is 0. So quite similarly, if you would be using a Kmap for every output, then in case of BCD to decimal decoder, the value of D0 would be 1 for the first minterm, which lies here in this square, and for all other square it would be 0. So the square in this map with the empty square are actually squares with 0, and these minterms are don't care. These input combination will not occur because in the BCD to decimal decoder, actually the BCD is 4-bit code, so the first 10 combination of the 4-bit code are used, but input combinations equal to 10 and above 10 are not used, so there are don't care conditions. And those input combinations, the minterms corresponding to those those input combinations are don't care, and they are represented with X, as we already know. So for the map and BCD to decimal decoder, the map for D0 would look like this. This box, this square would be 1, which is represented with D0 because we are using a single map, and all the empty square would be 0 and these square are don't care conditions. Similarly, if we would be using a Kmap for D1, then only the square related to the D1 min term would be 1, which is represented with D1 just to differentiate it from other min terms and other Kmaps, and all the empty squares would be 0 and the don't care conditions are the same. Similarly for D2, similar for D3, and similar is the case for D4 and for all other output variables of the decoder. And if we continue this, we eventually would come up with a single map, and this map actually is a compact map that represent all the output variables of the decoder. So in this map, we whenever we want to derive the Boolean equations of these variables, it is very simple. For example, whenever we want to consider D0, whenever we want to consider this map for the output variable D0, then just consider 1 in the square where D0 lies, and consider all other D's as 0 and the don't care conditions are don't care condition. So this D0 is 1 when we visualize to create Boolean equation for the D0, then this square has 1, all of the other D's are 0 and don't care conditions are represented with X. So this D0 is 1, so it cannot be grouped with any other square because it doesn't have any square that has a value of 1 and is the neighbor of D0. So it's a single square, and this group only contain one square. So the Boolean equation would be W prime and X prime, Y prime, and Z prime. So this is the first min term. D0 is W prime, X prime, Y prime, Z prime. Similarly, when we want to create the Boolean equation for D1, then the square which has D1 is considered to be 1 and all of the other squares with D's are considered to be 0. So like this, and this square is not a neighbor of any other square with 1 because only this square has 1 and all other square has either 0 or X, but neither of the X is a neighbor to this D1 square. So we can only make one single group of a single square. So the Boolean equation would be W prime, X prime, Y prime, Z for this group. Similarly, to continue with the D2, in this case, this don't care square is a neighbor of D2 because we are considering 4 variable maps. So when we roll our 4 variable map across this line, then this square is a neighbor of this square. So we can consider don't care squares as 1 to result simplified Boolean equations. So the simplified Boolean equation of variable D2 would be X prime, because X prime lies here and here, X prime, Y, and Z prime. So this would be the equation of D2, X prime, Y, Z prime. Similarly, if we continue like this for D3, then this square is a neighbor of X, and we can make a group of 2 squares. So this would give us the Boolean equation of D3 is equal to X prime, Y, Z. And for D4 is a neighbor of this X. So this is again a group of 2 squares, and the equation would be X, Y prime, and Z prime. And for D5, it can be grouped with this nearby X and 2 square group we have, and the Boolean equation would be X, Y prime, Z. Similarly, for D6, we can combine it with this square, so 2 square group, and the equation is X, x, y, and z prime is the equation for D6. For D7, we can combine it with this square, again 2 square group. So we have x, because x covers these two square, and y from the above level, and z. So x, y, z is the Boolean equation of D7. For D8, we can combine these two square with these two square to create a group of 4 squares. So the Boolean equation of D8 would be W and Z prime. So W Z prime is the Boolean equation of D8. And for the D9, we can combine these three don't care squares with D9, and it would give us D9 is equal to WZ. W would cover these 4 squares, and Z would also cover these 4 squares. So WZ is the equation of D9. So we have used the single map, but we have visualized that the single map actually represent 10 maps, 10 Kmaps. So we had the advantage of the decoder circuit, because this decoder circuit gives only one when an input is provided. So only one output can be one at one particular time. So this gives us the advantage to use a single map for all 10 output variables. Okay. Just to remind you, you can use a single map for every output variable. That approach is still valid, but a single map for all output variables is more efficient solution. Okay, so these Boolean functions can be implemented like this. D0, every, just like the decode 3 to 8 lines decoder, there are 4 inputs, and as these input variables appear in the normal form and complemented form, so it is wise to create normal form of these variables as well as complemented form of these variables, and then these outputs are generated from the AND gates, because these these Boolean functions are just AND terms, so they are achieved from the AND gate here. So this is BCD to decimal decoder. The input is a BCD 4-bit BCD code, and the output is a decimal digit. For example, when the input is WXYZ, that is 0, 0, 0, 0, then this code represent decimal 0. So the output related to decimal 0, which is the first output, is 1. All of the rest are zeros. And similarly for all other input combination. Okay, so as we saw in the initially in the 3 to 8 lines decoder, there were 3 inputs and 2 raised to power 3 outputs. So the outputs were equal to the maximum number of outputs. But in this case, there are 4 inputs, and we could have 2 raised to power 4, which is 16 outputs. But in this case, in this particular case, we have only 10 outputs, and this is because the 6 input combinations are not used in their don't care conditions, and this also tells us that the number of inputs, which is n, the number of outputs, which is m, is sometime less than 2 raised to power n, which is the number of inputs. So this can be the this is a unique example to highlight that aspect as well. Okay, so we can implement combinational logic with decoder, and this is a simple example to show you that a full adder can be implemented with a decoder. So we have already designed 3 to 8 lines decoder. This is 3 to 8 lines decoder. We have 3 input lines and we have 8 output lines, and whenever a 3-bit input is applied to this decoder, only one of the output lines is high and all of the other output lines are 0. So this is a 3 to 8 line decoder. Okay, so how can we implement combinational logic with a decoder? We must understand that a decoder actually creates all possible minterms. So in this case, 3 to 8 lines decoder, 3 are the input lines, and it generates 8 outputs, and each output corresponds to a minterm. And we have already seen that any Boolean function can be implemented as a sum of minterms. If it is not in the sum of minterms, it can be manipulated to sum of minterms. So sum of minterm is not a good representation of the Boolean function, but sometimes it is more economical to represent a Boolean function in the sum of minterms form. And in particular, if we are interested to implement a function with the MSI package. So this is an example which highlights that fact. We have 3 to 8 line decoder, and we want to implement a full adder. So a full adder has two outputs. One output is called sum output, and the other is carry. So a sum and carry, when they are represented in the sum of minterms, then we see that sum is represented with sum of minterms, and this says that the sum Boolean function is the sum of minterm 1, the sum of minterm 2, 4, and 7, and similarly the carry function is equal to the sum of minterm 3, 5, 6, and 7. As a decoder creates all possible minterms, then it is easy to use an OR gate and just combine these output of the decoder, as sum is equal to the sum of these minterms. So just combine these minterms from the decoder output through an OR gate, and that is the result that would give us S. So this is exactly done here. So S is there is an OR gate, and this OR gate combines the minterm 1. Minterm 1 is given to this OR gate. Minterm 2. Minterm 2 is given to this OR gate. Minterm 4. Minterm 4 is given to this OR gate, and minterm 7. Minterm 7 is given to this OR gate. So the sum bit of the full adder is sum of these 4 minterms, and we already have these 4 minterms from 3 to 8 lines decoder. Just give the 3 bit of audend and augend and the input carry to the 3 to 8 line decoder, and use an OR gate, and you would get the sum bit of the full adder. Similarly, the carry bit is the sum of minterm 3, 5, 6, and 7. So we just sum these minterm 3, 5, 6, and 7, and we get the carry bit of the full adder. So quite similarly, we can implement any Boolean function, any 3 variable Boolean function with 3 to 8 line decoder. A 3 to 8 line decoder, we have 3 variables. Their total possible minterms are 8, and any Boolean function, any 3 variable Boolean function can be implemented with 3 to 8 line decoder. Just we would need an OR gate to implement a single Boolean function, and would combine the minterms of the decoder that makes that function. Okay, so decoders, 2 to 4 line decoders using NAND gate. As I initially mentioned, that a decoder can also be implemented using NAND gate, and this is an example of 2 to 4 lines decoder. And this 2 to 4 lines decoder is different than a conventional decoder in these 2 places. The first point is that the decoder, this decoder is implemented with NAND gate. Previous decoders were implemented with AND gates, and there are small circles after these AND gates which make them NAND gate, and these circles actually inverts the output of these AND gates. And similarly, there is an additional input given to all these AND gates, and this input is called enable. So whenever this enable is 0, this line would give a 1 to all these and NAND gates, and whenever this enable input is 1, then these NAND gate would get at least one input from this enable as 0, and whenever this gets a 0 input, the output would always be 1, which is shown here. So we have two inputs, and these two inputs are connected to these NAND gate, and these are the 4 minterms, because we have two variables, so 2 raised to power 2 is 4, so we have 4 minterms. There are NAND gate which inverts the output of these AND gates, and there is an enable line. This enable line enable or disables these NAND gates. So how it works, let me show you the truth table of this 2 to 4 line decoder implemented with NAND gates. Okay, so whenever the enable line is 1, we will get 0 here, and this 0 will disable all these NAND gates. So whenever the enable line is 1, regardless of the two inputs A and B, the output of all these D0, D1, D2 and D3 would be 1. Why? Because this E is 1, so we get 0 here. So we get at least one input to these NAND gates as 0, and the output of these NAND gates would be 0, but this inverter would make them 1. So D0 would be 1, D1 would be 1, D2 would be 1, D3 would be 1. So whenever the enable input is 1, regardless of the two inputs A and B, the output would be 1. So whenever enable is 0, we would get 1 here, and the output of these AND gate would depend on the input A and B. So whenever E is 0 and the inputs A, B changes. So when A and B are 0, 0, only D0 is 0, the rest of outputs are 1. Whenever keeping E as 0, whenever A, B changes to 0, 1, the D1 is 1. When it changes to 1, 0, D2 is 0. When it changes to 1, 1, D3 is 0. So only one of the outputs is 0, all the rest of the outputs are 1, and this is because of the NAND gates. In the case of AND gates in 3 to 8 lines decoder, I just discussed a few slides back, only one of the outputs would be 1, all of the other would be 0. But in the decoder implemented with NAND gate, only one of the output is 0, all of the other are 1. Okay, so this is a 2 to 4 line decoder implemented with NAND gates. Okay, so demultiplexers. This is a 2 to 4 line decoder, and this is the block diagram of that 2 to 4 line decoder. We have two inputs, A and B are the two inputs, and there are 4 NAND gates. In fact, they are AND gates, but the circles are shown here. These are the 4 outputs. There is an enable. This circle shows the inverter. So this is the same decoder, 2 to 4 line decoder shown here. So this is the detailed version of the 2 to 4 line decoder, and this is the block diagram of the 2 to 4 line decoder. We can make a demultiplexer from this 2 to 4 line decoder. What we need to do is to invert or swap these two inputs with the enable. Just bring this enable here and bring these two inputs here, and we call these two inputs as select, and we call this enable as input. like this. So what we do here, this is a 2 to 4 line decoder, but this enable is brought here, and this enable is now called input, and these two inputs are brought here and they are called select. So what this demultiplexer does, it gets one single input, and these select lines chooses one of the 4 output lines and directs this input to these output lines. So this is a 1 to 4 line multiplexer. So this demultiplexer, sorry. So this input, single bit input, is demultiplexed towards any of these 4 lines, and these 4 lines are selected by these two input select lines. So for example, if the value of AB is 0, 0, then this input is directed or connected to D0. Whenever AB is 0, 1, this input is connected to D1. Whenever AB is 1, 0, this input is connected to D2. Whenever AB is 1, 1, this input is connected to D3. So this is the function of demultiplexer, 1 cross 4 demultiplexer. This kind of decoder with an enable pin, if we have a 3 to 8 line decoder with the enable pin, such a decoder can be reused to design a bigger decoder. For example, 3 cross 8 decoder may be used to create a 4 to 16 lines decoder, like this. The enable pin, we have 3 to 8 line decoder. The 3 inputs X, Y, Z are connected with the 3 to 8 lines decoder. We have D0 to D7, 8 outputs, and we have another decoder, and the same 3 inputs are connected to the input lines of the 3 to 8 line decoder. But the enable pin, there is a 4th input is connected, and that 4th input is directly connected with the lower decoder, and it is connected after the inverter with upper decoder. And we just mark or label the output of the second decoder as D8 to D15. So whenever W is 0, the upper decoder is selected. These 3 input lines would select one of the 8 output lines of the upper decoder, and whenever W is 1, the lower decoder is selected, is enabled, the upper is disabled, and these 3 input lines would select one of these 8 outputs of the lower decoder. So in reality, these 4 lines would select any of these 16 outputs. So we have 4 inputs, and one of these 16 outputs are selected. So we have 4 to 16 lines decoder.